right? So we did an averager, and then it kind of like, then it took the sharp edges out, right? That's just one use case, right? You can have whatever you want, right? Because what this, y of n equals, so that one was like 1 summation k equals 0 to m, right, which is 2 s of n minus k, right? Yep, okay. Is that, it goes to the n values behind it, right? And then kind of averages it out, right? So for this one, it was just an averaging case. But we later in the recording, right, I said, well, you can really generalize this to be this, just a b of k. Oh, you kind of plot this guy in here. Just say it's a summation, k equals 0 to m. This b of k times x of n minus k, right? And this b of k could be anything, right? It could be, for that one, our b of k was, 1/3, 1/3, 1/3. But in the homework, I think you have one that's kind of weighted to the front. So that's gonna be like 1/7, 1/14, whatever, right? I don't remember exactly the coefficients were, but it's basically given more value to the present data versus like past data. And really any filter can be whatever you decide it to be, right? For this one, it was just, if you have this high frequency, like let's say you want to sharpen down, right? Take away some of the frequencies or the higher frequencies, you can just do an averager, right? At these spikes, and you can kind of like mellow it down. You are going to change the frequency component, but if you don't care about that because those frequencies are not of interest to you, right? You just kind of want to clean up the data for a given window, right? You would find out whatever that b of k for that specific, place is, right? 3 data points might not be enough if you're sampling at, 9 gigahertz or whatever, right? You might need 1,000 data points, which, when you're looking at 9 million data points per second, it's, 1,000 data points is not a lot, right? Which is why you use a computer to do that. You wouldn't want to do that by hand, right? So when I said no, it's just because that was just one specific case. But, you use the idea of the summation equation to kind of open up the Pandora's box of filtering or of manipulating the data, right? In order for you to get to your end point, right? So it's this, averager, everybody knows what an average is, right? I add a bunch of things and I divide it by as many things as I'm averaging, right? It's a very intuitive, which is why you start here. Because everybody knows what an averager is, right? And then we write it in this mathematical way, and then we decompose it, and we're like, well, we can make a very general sort of like equation with it, right? And then, I don't know, your B of K could change, and you could have different B of Ks. The length of, the order of your filter is going to change. You can have larger order, et cetera, et cetera, et cetera, right? And then shit got really bad, right? And then we started talking about the unit impulse, right? And the unit impulse helps us further generalize filters and helps us further think about it in a more technical kind of mathematical way, right? Because then it allows us, for example, if you have a black box and you don't know what that engineering thing is, right? You can send the unit impulse and then you can just send a whatever voltage at the certain frequency. And whatever you read out, you can speculate that's the impulse of the system, that's your impulse response, right? And then you can take that impulse response and be like, okay, this is what this black box does, right? So if I put this input, I'll get this output, right? Or if I want this output, this is the kind of input that I'm gonna have to put in, right? So it's even though like looks shitty or whatever, right? It really is more of a like how to be able to do it in both ways, right? Once you understand that a system is this, right, and you're able to decompose a system into various components, then then you can start manipulating those components to get, you know, whatever it is that you want out of it. Or you can predict what you're gonna get out if you know what you're putting in and you know what that unit impulse is, right? And then you can start building systems around it, right? So the whole idea of starting with this, you know, averager and then generalizing it is really to get us to that, you know, impulse response, which, you know, we'll talk about, right? So, sorry, the unit impulse. So the unit impulse, unfortunately there's too many ends, right? Which is what it was kind of, I was like going back and forth, like trying not to confuse everybody, not trying to confuse everybody. But the unit impulse is this theoretical, it's very theoretical. It's not realizable because it is, you know, it's denoted by this delta, delta of n. And it is simply 1 when n equals 0. N at this point is just whatever's inside here. Just remember that, okay? And it's 0 otherwise, right? So when you plot this out, right, you end up with a very narrow and sharp 1, and then a bunch of zeros. And the reason it's not, I say that it's a theoretical, is that it's not realizable. There's no way to get like nothing, then something, then nothing, right? Like there has to be some kind of ramp up and ramp down sort of thing, like in real life, right? But from a theory point of view, it's a very useful tool to create, right? So some mathematician created it in order to like then allow us to extrapolate further, right? So, you know, then we said, all right, well then x of n can be rewritten by the summation, you know, from k to negative infinity, assuming that it's like an infinite sort of thing, which we know it's not, but again, this is more math conversation, right? This x of n minus k, right, times delta n minus k. Okay?
I think that's the y of n on the left.
No, it's x of n.
Oh, x of 1 on x of 1.
Well, yeah, because like,
Okay.
you're just multiplying by 1 where that's satisfied, right? Hold on. How does this work? Because basically what it ends up going, sorry, I thought about it yesterday and I haven't thought of it again. But x of n is x of k. Sorry,
X of
you're right
k.
here. X of k, that's where I got it wrong. X of k, yep, times whatever that shift is, right? So, you know, you have this n, which is, you know, whatever you want it to be. This, 0, and then this huge thing, right? And then for each individual x of k, it's basically you multiply it by that delta at that given shift, right? So it's just times 1 the whole time. And we know that anything multiplied by 1 is just itself back in, right? And then we said that, again, right, when you have this x of n goes into some kind of system, right, some discrete time, right? So this is not infinite, this is at a specific time, a discrete time, right? For every y of n, you're gonna get a corresponding y of n at that discrete time, right? Which is very important to understand that this is a discrete time FIR filter. Which I think not this one is tau. I think I have to, I hate Greek, so I don't care. Right? So, you know, we had said that, okay, this is kind of like the black box we were talking about earlier, right? If you put a unit impulse, which is just 1 wherever it meets anything, right? If it's 0, it's gonna be 0. If it's something, it's gonna be something. So you put this unit impulse into this black box, what you end up getting is that impulse response, right? Okay. So far, any questions here? Again, this is just a mathematical construct. At this point, like, none of this is realizable. Anything times 1 is itself, so all this kind of follows. Okay. then we take this original, this kind of thing that we talked about, this very generic y of n equals the summation k equals 0 to m b of k times x of n minus k, right? We take this, okay, yep. Okay. Then, when you put an impulse, you get your h of it, right? So you're gonna get the corresponding impulse response to the system, right? So then your h of n becomes the summation, right? From k equals 0 to m b of k times delta n of k, right? Because we know that this y of n, right, was this x of n with whatever that black box did to it at each individual impulse, right? So this b of k then, we know that it's gonna be, if you didn't put an h of n, if you just put a delta 1, those b of k's are gonna come out, right? So this b of k then becomes this h of n then becomes that summation of those b of k values, right? Depending on what that system is doing to the overall x of n sort of thing, and I know there's a lot of variables, right? Where, again, right, it's gonna be b of k, where n equals 0, and then 0 otherwise. Okay? And then we marry these two, right? Because we love to do those kind of things. Then we say, okay, fine. Then our y of n can be written, right? K equals 0, summation, m-order filter, h of n times x of n minus k. Right? Because just going to be your b of k mass once you do that, right? Because we said your x of n for this is just x of n, and if your b of k that, then it's just your b of k. So simple, right? Okay. So now we have a relationship where your y of n is, your h of n times your x of n, right? It's a filter coefficient between your input and the impulse response. And this is called, this guy. This is where you're gonna get your response for it. Number 2 is, this is your finite convolution sum. And this is a pain in the ass to actually execute, right? And there's multiple ways to do it, and we're gonna go through 2. You're gonna be expected to know them by the exam time. So, good luck. Okay, so this is where everybody kind of messed up in the exam, so I'm gonna weigh it a little bit less this time, and I'm gonna put extra credit. I'm going back to fail or punish you guys, but I do have some tests to do. Shit. Which is how you can get an A plus in this class. Honestly, okay, so have you guys looked at the syllabus? Right, A starts at 90, just so you know. Right? And And then in order for you to get like a B minus, you gotta get like below, in order for you to get a B plus, you gotta get like below 87, right? So this class is hard enough, I know this, right? So the weights are weighted down, right? Because this stuff's not easy, right? So, okay, anyways, I just wanted to make sure that's clear. Let's see. So, okay, let's do convolution example. Let's do an example. But we talked a lot, let's actually do an example. What if I gave you h of n is delta n minus 3? How would you set that up? Actually, no. Two things. First, find h of n. For x of n from n equals 0, 1, 2, 3, 2, 1. Solve for y of n. And C is going to be plot x of n and y of n. Go. 3 minutes. You done? Okay. Who wants to actually try it and who wants to just go for it?
Yeah, I think I'm done.
You want to try it?
Yeah.
Okay. Are you solved it already?
I mean the first one, yeah.
Okay. Yeah, give me the first one then.
So everything is 0 except 3.
Yeah, that's right. Yeah. So delta n shifted, right? So at 3, 1, everywhere 0. Good. Okay. Who wants to solve the second part? All right, cool. Take your time.
So basically this was just n minus 3, right? So this would be, let's have it convoluted. And then if it's correct, choosing 2. Did I do that right?
Not really. I don't know how you got there.
Minus n minus 3, so 1 minus 3, 2 minus 3.
No. So,
Okay, it's 2.
no. So, that's not quite it, right? Because you're missing the step of, okay, so let's set it up here. What's y of m? From just our equation there. Summation k equals 0 to m, right? H of n. Okay, yeah? Okay, so this is our h of n, right? For which value is it not 0? For 3, right? Well, let's try, okay, so let's say it's at 0, right? So if we were to start at 0, it would say h of n, so it would be h of 0 times x of n minus 0, right? And the summation, now k equals 1, h of one, x of n minus one, right? Alright, summation times two, h of two, x of n minus two, summation, increment, three, h of three, x of n minus three, right? And then we'll just do one more just for shits and giggles. Summation, k equals four, h of four, x of n minus four. Okay. I'll ask again. For which values is x of n not zero? So what's h of zero?
Zero.
Zero. Anything times zero? Nothing. What's h of one?
Zero.
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 H of two?
Zero.
H of three?
One.
H of four?
Zero.
So what's our y of n? So what does that mean? It means that this is where you plot x of n, right? X of n is 1, 2, 3, 2, 1, starting at n equals 0, right? And then 1, 2. For y of n, we're gonna get this x of n back, right? But it's gonna be shifted, what? 3 which way? That way. So it's gonna be 1, 3 from 0, so it's gonna be 1 and 3. And then 2, 3. Right? And then 0 everywhere else.
So that x of n, the one on the left, and y.
Yeah, this is x of n, right? As I said, it starts at n equals 0. And our y of n is that same x of n, but just shifted to the right by 3. This is actually a very important property. And it'll come back to bite you in the ass. Actually, it's just one of those things that it's gonna keep, there's a time aspect to it, and there's also a frequency aspect to it as well. But for now, it's just, the output is the same as x of n, except delayed by 3. So it ends up being that that's actually called a delay filter. Delay. Right, so when h of n equals delta of n minus n naught, right? N naught is an integer. It's a filter with an n naught delay. Okay, that's a property. Okay? And so for this example, what's our n naught? For that one? 3, right? So we divide by 3. What if I gave you an h of n delta n plus 4? What would your n naught be?
Negative 4.
Negative 4, right? Which means you're shifting back in time, right? If it was a time sort of thing, but this would be negative 4. So it could be positive or negative, depending on the data is being captured. You can't really go back in time, but if it's already data, whatever. There's for non-causal filters it won't work, but for causal filters it will work. But anyways, so this is just delay filter. It's a very important property. Okay, so that's an easy convolution because it's just one function, right? Okay, great. What?
Oh, wait. You have a C, S of n plus y of n. Is he adding on top of each other?
and. This one you mean?
Oh, yeah.
It's not plus, it's just, that's just how I write and. I
Oh,
write ands like
okay.
This
I
is
thought
my
it was
and.
close. Oh.
And this is my zeros.
So I have a question.
Yes.
How do you put x of n and y of n?
Okay, so remember that in the beginning of class I talked about the general pulse, right? And how it is that you shifted it. So, you know, for x of n, when it's kind of like the delta n, when whatever is inside here equals 0, then it's 1. When whatever inside here equals 1, then it's 2, and so forth. So if y of n equals x of n minus 3, when what, how can I ask? For what n value will you get x of 0?
So how do you know the magnitude of what, like y2 is in x of n, y2 is larger than 1, 0.
Okay, so everything here is 0. This is your x of n. I just kind of plotted it. So this is 1, this is 2, this is 3, this is 2, this is 1. This is 1, this is 2, this is 3, this is 2. It's the exact same x of n, but it's shifted forward in time by 3 n's.
But how do you know the magnitudes?
Because it's just your x of n. It's just x of n. So I told you, so this is x of 0, this is x of 1, this is x of 2. It's kind of like an array sort of thing, right? This is x of 3, this is x of 4. Okay? Each individual component is a place value for that array. So which is why I asked you, for what n value will you get x of 0? What's the answer?
What's the, say that again?
For what n value will you get x equals 0?
3?
Yeah, 3. So at n equals 3, you get x of 0, which is 1. And then for x equals 1, it would have to be 4. Right? That's how you know you're shifting forward in time, which is why when we talked about at the beginning why it's minus and we go this way and you would think it'd be the opposite, it has to do with these sort of things, right? It's I know it's hard to like wrap your head, but just think about it some more and then have everybody explain. If it's not the first time, we gotta keep going. But just keep thinking about it. But it's just we're basically trying to get these x of 0s back given this information now. It's the same x of n. The amplitude's going to be the same. It's now just shifted 3 data points that way. But we're not doing 2 times x of n. It's just x of n, honestly. Right? You could amplify, but we didn't. Okay. Yes, we got 30 minutes. Because this is where the fun starts. It's easy when it's just 1. Not so much, yes. When you have more. That's when you really start getting me. Okay. All right, let's do our second example. Well, before we do that, let's just okay. So I said that y of n equals this. One just important thing to understand is that when this expression goes to infinity, that's called convolution, right? Which is why this is finite convolution. Like the true term of convolution, it's y of n equals the summation from k equals negative infinity to infinity, h of n, x of n minus k, h of k. Okay? Which is rewritten as h of n convolved with x of n. And this is where you'll see, it's not like a multiplication, it's just like asterisk, and it just means convolution, right? we don't live in the infinite world, right? We live in the finite world, right? The convolution still applies. And today we're just gonna introduce it. When we come back after the exam, we'll see that there are properties that are beneficial. So when you have cascading systems, you can actually like put them all together using these convolution properties. So it's an important topic to have. But just understand that this is what if you ever see this kind of writing, this is what it's talking about. It's talking about this infinite that then we apply to the finite. Okay? And this is convolution in its most general form. And I'm writing sideways because I need more space. But that's finite convolution. That's the kind of thing that we'll be doing. Okay? I just want to make sure that I write that before I forget. Okay. So let's all right. Okay, so what if I give you an h of n equals 3, -1, 2, 1. And I give you an x of n equals 2, 4, 6, 4, 2. And I ask you, solve for y of n. And just, we're very explicit. N equals 0. N equals 0. Okay, let's first do an explicit form, alright? So y of n equals summation, right? From k equals 0 to m h of k x of n minus k. Okay. So what's our m here? Right, so it's the length minus 1, right? So this is actually 3. Okay. So from a very explicit way, it's h of 1 times x of n, or h of 0 times x of n, plus h of 1 times x of n minus 1, plus h of 2 times x of n minus 2 plus h of 3 x of n minus 3. This is a very explicit way to write it, right? For everything else, I don't care because it's going to be 0. Okay? Start at 0 all the way to 3. Which means that this is 3 times x of n plus, I guess, minus x of n minus 1 plus 2 times x of n minus 2 plus x of n minus 3. This is your y of n. Okay? Yes?
Is it normal for the numbers to be not organized?
Not organized. You mean your h of n?
I mean, yeah, and even like x of n.
Yeah, of course. I'm gonna give you what the hell I want. I'm not gonna give you 1, 2, 3, 4, 5. Why would I do that?
I mean, like, that one is 3, then -1, then 2, then 1. Like, should it
Sure,
be
yeah, I
like-
can do whatever I want.
Okay.
I'm the professor. I can put 0, 0, 0, 3, 3, 3, 2, 0, 0, 0, 0, 1, 4, 4. It doesn't matter. Right? The idea itself should be the same. Right? Okay. fine, alright, shit, this sucks, but fine, okay. This is what it looks like. Before we start to solve, I just kind of want you guys to see the bigger picture. What does this mean, right? This means that for y of n in total, it would be 3 times this x of n, right? Whatever that is, right? So y of n at the end. And then it would be minus this x, the same x of n, but shifted this way, like that way, right? Plus 2 times this x of n, shifted now to that way, plus x of n minus 3. And the reason I'm kind of scaling them that way is that you can create a table with this, right? So if you wanted to get the overall y of n, what I would suggest that you do is you create a table, right? Can I erase this? And the way you do that, I asked you, let's say on the exam, I gave you this very arbitrary h of n, a very arbitrary x of n, and I said, solve for y of n. This is how I would do it, because there's another way to do it, and I'll show you, but I hate it. Okay. What I would do is I would set up a table. You have your n values at top. You have 0, 1, 2, 3. And you know where to stop because you know how far away you shifted. So you shifted 3 that way. The length of it is 5, so I'm going to stop at 7. 4, 5, 6, 7. And then what I'm going to have is I'm going to have an h of 0. Actually, first I'm going to have an h of n. I'm going to have an x of n. Just kind of my starting points here. This, and then like this. That's very ugly. Okay, this is how I would set up my table. And this is actually how the book shows it. So if you need a better drawing, go to the book. All right, and then what I would do is I would say h of 0, x of n. Then I would say h of 1 times x of n minus 1, h of 2, x of n minus 2, and then h of 3, x of n minus 3, okay? Then I would delineate it, and then I would say my y of n. Then what I would do is I would put my h of n, so I would say this is 3, this is negative 1, this is 2, this is 1. Come on, can you, somebody, 2, 4,
6, 4, 2.
4, 2. Okay. And then what I would do is, I already know that before this zeros, x of n this one, x of n that way. Because it's shifted, I'm just going to put 1 0 here for n minus 1, and 2 zeros here, and 3 zeros here, so I don't lose my place. Okay? This is what I do. Okay, what's our h of 0? 3. What's 3 times 2? 3 times 4? 3 times 6? Is this all you? Nobody else knows how to do arithmetic in this class. Somebody other than Gentry. 3 times 4?
5.
Oh. If you said 5. Okay, and then you just, for the next one, is negative 1 times everything. So you just negate everything. Okay? I'm kind of starting to drift, and I don't like that. So let me, I want to be as, because it's going to okay, so this was 6. Maybe this is the one that I need to move, actually. Negative 6, and then negative 4, and then negative 2. Okay, well, h of 2 is 2, so I just need to double everything. So this is 4, 8, 12, 8, 4. And then it's just 1 times it again, right? 2, 4, 6, 4, 2. Go ahead.
I got confused. Can you explain
Of course.
how you got the numbers?
I'm using this, translating it to this, and then applying it here. Because y of n is going to be the summation of h of 0, h of 1 times x minus 1, h of 2 times x n minus 2, h of 3 times x n minus 3.
So it's basically plug and chug, right?
So all you do is, you get your h of 0, which is 3, and then x of n. So x of n is just this times 3. And then you say h of 1 n minus 1, well, that means now this x of n got shifted 1, and then it got multiplied by negative 1. Right, which is why I'm being very explicit the way I write it. And then for this h of 2, then it's h of 2, which is 2 times the same x of n, but shifted over twice. And then h of 3 is 1 times this x of n, but shifted over 3 times. So it keeps it in a very regular order, because then what is y of n? Y of n is the summation of 3 times x of n minus x of n shifted 1 plus 2 times x of n shifted 2 plus x of n shifted 3. So all you do now is you just add 6, 10, 18, 14, 18, 12, 8, and 2. And if I did some math wrong there, I apologize. Okay? That's how you solve for y of n in this table format.
Dang, that's crazy.
Okay?
No wonder I said a lot of people make mistakes.
A lot of people. Okay, I prefer this method. Okay. Another method you can use is what's called, and I hate the shit out of it, but some people like it, right? Like the professor who taught me loved it. I hated him for it, but it's okay. I'm glad I read the book because he didn't even go over the table thing.
Wow.
The book is the one who introduced the table.
No, no, it's-
Okay, go ahead. I'm not gonna erase it. No. Okay, so what he chose to teach was that what he calls it is this flip, drag, add.